We're going to get some practice dealing with acceleration by calculating how much time it takes for a bus to come to a complete stop. So imagine we have a bus on a road. The speed limit is 13.4 meters per second. Very convenient that they listed it in SI units. So let's say that the bus's initial speed is that. Its final speed is going to have to be 0 because we want it to come to a complete stop. So we'll assume that it experiences a constant acceleration going from the initial speed of 13.4 meters per second to the final speed of 0. Let's further assume that the positive x direction is to the right. Now we need to know something about the acceleration of this bus. Let's say we looked up the specs of the bus and they decided that a safe acceleration was 1.5 meters per second squared. Now you'll notice that I've written a equals minus 1.5 meters per second squared. Well, I said that the positive x direction is to the right. Certainly the bus's initial velocity was to the right, so if we want the bus to slow down, its acceleration has to be to the left, which is a negative number. So we already said the initial velocity is 13.4 meters per second. That's positive. Final velocity is 0 meters per second. And we can use an expression for acceleration to figure out how much time it takes to stop this bus. Now, the calculus version of this looks a little involved. We don't have any functions to differentiate. But remember, if the acceleration is constant, you can turn this into a ratio of differences, right? You can turn the derivative into delta Vx over delta t, namely the change in velocity over the time interval. Well, the time interval, delta t, is exactly what we want to solve for, so let's do that now. I'll rewrite that equation over here on the right. Let's multiply both sides of that by delta t and divide both sides by the acceleration to isolate delta t. We'll expand delta v to be vf minus v naught, and now we can just put in the numerical values. Remember, final velocity was 0 meters per second, the initial velocity was 13.4 meters per second, and the acceleration was minus 1.5 meters per second squared. Now you can see it's important that we track those signs because we're going to end up getting that the sign of 13.4 and the sign of 1.5 cancel so that everything comes out positive. We expect a positive time interval in the end, and indeed we'll get it. Divide those two numbers and we get out that the time interval is 8.9333 seconds. Let's round that off to 3 significant digits as appropriate. So the time interval is 8.93 seconds. That's how long it takes for the bus to go from a speed of 13.4 meters per second to a speed of 0, assuming a constant acceleration of 1.5 meters per second squared in magnitude. A reasonable follow-up question is how much distance is required to stop this bus? So we know that it takes 8.93 seconds of time, but how far in advance of the stop sign would the bus driver need to start applying the brakes in order to actually reach a stop at the stop sign with that acceleration? Well, to figure that out, we'll need to use one of our 1D equations of motion, that one over there. Let's write that out. And all we really need to do is solve for the displacement delta x, right? That's the distance over which the bus will be stopping. So our first step in isolating delta x is to bring the initial velocity squared over to the other side. So we subtract that from both sides. And now we'll just isolate delta x. So we solve for delta x. Now all we need are the numerical values of the final velocity, the initial velocity, and the acceleration. Well, of course, we used those for the previous problem, so we can just plug those numbers in. Final velocity is 0, initial velocity was 13.4 meters per second, and then the acceleration was minus 1.5 meters per second squared. We really need this bus to get out of the way, so I'll move that. And now let's simplify this expression. So we get rid of the 0 squared, we'll cancel the negative signs, and square 13.4 meters per second. Now you can see that the units of this are going to be meters squared per second squared, divided by meters per second squared. The only thing left will be meters, which is of course what we expect when calculating a displacement. So we get 59.8533 meters. Let's round it off to the appropriate 3 significant figures to see that delta x equals 59.9 meters. So the bus driver would have to start applying the brakes nearly 60 meters in advance of the stop sign with an acceleration of magnitude 1.5 meters per second squared in order to stop by the time they get to the stop sign.